Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries, and we are on day 18 of the hashtag 30 Days of Code Challenge with Educative. I have a fun one for you, and it's an easy one. Merge two sorted lists on LeetCode. So let's get into this walkthrough. Today, we're tackling a classic linked list problem called merge two sorted lists. This is labeled as an easy problem, but don't let that fool you. It teaches foundational skills that show up in every single data structure interview. Master this and you'll have the building blocks for much harder problems. We're given two sorted linked lists. Our job is to merge them into one sorted list by rewiring pointers, not by creating new nodes or copying values. At the end, we return the head of this newly merged list. The emphasis here is on pointer manipulation. You're not allowed to create new nodes with new values. You must reuse the existing nodes from the two input lists and just change where they point. Before we dive into merging, let's make sure we're on the same page about what a linked list actually is. A linked list is a data structure made up of nodes. Each node contains two things: a value, which is the data stored in that node, and a pointer to the next node in the sequence. Unlike arrays, linked lists don't support random access. You can't just jump to the fifth element. You have to start at the head and walk forward, following the next pointers one by one. This is why pointer manipulation matters so much in linked list problems. You're constantly rewiring these next pointers to build new structures. Let's look at the classic example to see what merging looks like. List 1. 1 arrow, 2 arrow, 4. This is a sorted linked list with 3 nodes. List 2. 1 arrow, 3 arrow, 4. Also sorted, also 3 nodes. After merging, the result should be 1 arrow, 1 arrow, 2 arrow, 3 arrow, 4 arrow, 4. Notice that all 6 nodes from the original lists are present in the merged list. Here's an edge case to keep in mind. List 1 is empty. It's just null and there's no nodes. List 2 is 0 arrow null, one node with the value 0. After merging, the result is just list 2, which is 0 arrow null. This reminds us that the algorithm needs to handle empty lists gracefully. If one list is empty, the merged list is just the other list, and there's no merging necessary. Let me give you the human intuition for how to merge these lists. Imagine you have 2 pointers, one pointing to the current node in list 1 and one pointing to the current node in list 2. At every step, look at the values. Pick the smaller value. Attach that node to your merged list. Move the pointer of that list forward to the next node. Repeat this process until both pointers reach the end of their respective lists. This is exactly what the algorithm does. 2 pointers compare values, attach the smaller one, move forward. You might be thinking, why not just copy all the values into an array, sort the array, and build a new linked list from that sorted array? Here's why that doesn't work. First, it breaks the rules. The problem explicitly says to merge by rewiring pointers, not by creating new nodes. Copying values and creating new nodes is not what the interviewer wants to see. Second, it's inefficient. Sorting an array takes all of n log n time, but the lists are already sorted. So you're throwing away that information and doing unnecessary work. Third, it ignores the fundamental skill the problem is testing, which is pointer manipulation. This problem is designed to test whether you understand how to work with linked lists at a low level. So the array approach is wrong on multiple levels. Here's the key insight that makes the solution simple. The two lists are already sorted. You don't need to sort anything. You just need to walk through both lists simultaneously and pick the smaller value at each step. No sorting, no extra data structures, and no complicated logic. Just 2 pointers and a comparison at each step. This is the beauty of working with sorted data. The structure is already there. You just need to merge intelligently. The most important trick in this problem is the dummy node. Let me explain why it matters. When you're building a new linked list from scratch, you have a problem. Where do you start? The first node you attach becomes the head of the list. But handling that first node requires special conditional logic. Like, if this is the first node, set head to this node. Otherwise, attach it to the previous node. The dummy node eliminates that complexity. Here's how it works. You create a fake node at the beginning, before any real nodes. You call it the dummy node. Then you attach all the real nodes to dummy.next. At the end, you return dummy.next, which is the actual head of the merged list. The dummy itself is discarded. This trick avoids awkward, is this the first node? Conditional logic. Every node, including the first real node, is treated the same way. Attach it to tail.next, then move tail forward. It's a small trick, but it makes the code much cleaner. Let me walk through the merge algorithm step by step. Start with a dummy node and a tail pointer. The tail pointer tracks the last node in the merged list so far. Initially, tail points to the dummy. While both list 1 and list 2 are non-empty, do the following. Compare list1.val and list2.val. If list1.val is smaller, attach list1 to tail.next. Then move list1 forward to list1.next.
If list2.val is smaller or equal, attach list2 to tail.next. Then move list2 forward to list2.next.
After attaching a node, move tail forward to tail.next. Eventually, one of the lists will become empty. When that happens, the while loop exits. At that point, attach whatever list still has nodes to tail.next. If list 1 still has nodes, attach list 1. If list 2 still has nodes, attach list 2. If both are empty, that's fine too. Tail.next will just be null. Finally, return dummy.next, which is the head of the merged list. Here's the clean Python solution. Let me walk through this code line by line. We create a dummy node with no value. This is our fake starting point. We create a tail pointer that initially points to dummy. Tail will always point to the last node in our merged list. We enter a while loop that continues as long as both list 1 and list 2 are non-null. Inside the loop, we compare list1.val and list2.val. If list 1's value is smaller, we attach list 1 to tail.next and move list 1 forward. Otherwise, we attach list 2 to tail.next and move list2 forward. After attaching a node, we move tail forward to tail.next. After the loop, one or both lists might be empty. We handle this with a single line. Tail.next equals list1 if list1 is non-null. Otherwise, list2. This attaches any remaining nodes. Finally, we return dummy.next, which is the actual head of the merged list. Notice how simple and readable this is once you understand the pattern. Let's analyze the complexity of this solution. The time complexity is O of n plus m, where n is the length of list 1 and m is the length of list 2. We visit each node exactly once. Each node is either attached to the merged list or skipped because it's null. No node is visited more than once. The space complexity is O of 1. We are not creating any new nodes. We're reusing the existing nodes from list 1 and 2. The only extra memory we use is the dummy node and the tail pointer, both of which are constant space. This is optimal. You cannot merge two sorted lists faster than O of n plus m because you must at least look at every node to know where it goes in the merged list. There's also an elegant recursive solution worth mentioning. Here's what it looks like. This is beautifully concise. The base cases are, if L1 is empty, return L2. If L2 is empty, return L1. Otherwise, compare L1.val and L2.val. If L1 is smaller, attach the result of merging L1.next and L2 to L1.next and return L1. Otherwise, attach the result of merging L1 and L2.next to L2.next and return L2. This recursive solution is elegant and intuitive, but it has a downside. It uses O of n plus m space for the recursion stack. Each recursive call adds a frame to the stack, and in the worst case, you have as many frames as there are nodes. The iterative version uses O of 1 space, so it's preferred in interviews, but the recursive version is worth knowing because it shows a different way of thinking about the problem. Let's talk about edge cases you need to handle. First, one or both lists empty. If list 1 is empty, return list 2. If list 2 is empty, return list 1. If both are empty, return null. The dummy node trick handles all of these naturally. Second, lists of unequal length. One list might have 10 nodes, the other might have 3. After the shorter list is exhausted, you just attach the rest of the longer list, and no special handling is needed. Third, duplicate values. Both lists might have the same value. The algorithm handles this by attaching one, then the other, in the correct sorted position. Fourth, single node lists. A list with just one node is still a valid list. The algorithm works the same way. The dummy node pattern is robust and handles all these cases without any additional conditional logic. Today's fundamentals are critical. First, linked list pointer manipulation. Understanding how to rewire next pointers is a foundational skill for every linked list problem. Second, using a dummy node to simplify logic. This eliminates special cases for the first node and makes your code cleaner. Third, merging sorted structures efficiently. When data is already sorted, you can merge in linear time and no sorting is needed. Fourth, understanding iterative versus recursive trade-offs. Recursion is elegant, but it uses stack space. Iteration is more space efficient. Fifth, building good instincts for list-based problems. Once you understand the dummy node trick and two-pointer merging, you can apply these patterns to many other problems. This is one of the most important foundational problems in the linked list category. Master it and you'll have a solid base for everything else. And that's a wrap of day 18 of our hashtag 30 Days of Code Challenge with Educative. If you like this video, like it down below, share it with a friend, comment, subscribe to our YouTube channel. We will be bringing a lot more breakdowns for you. We are almost 2/3 of the way through this competition, so super excited. And we will be sharing more breakdowns shortly. So we'll see you soon.